Gallium nitride on gallium nitride is one way to utilize the properties of gallium nitride as a material to the fullest.
Vikas comes from NexGen, which has a disruptive way of approaching GaN, which is GaN-on-GaN. So in our community of design engineers, I know that we have a lot of power design engineers who will be fascinated with you explaining, if you'd like to explain the difference to your approach to GaN electronics first, and then we can talk a little bit about the board.
Yeah, we'll be happy to, Guy. Thank you for having me. For the community of power electronics, I think you are no stranger to gallium nitride as a material. But for those who may not know what GaN on GaN is all about, it's important to kind of look at the entire power electronics industry from a historical perspective, and why NexGen believes that vertical gallium nitride or gallium nitride on gallium nitride is the technology to use for all power electronics going forward. So historically, all power electronics have been driven by silicon power transistors. What silicon power transistors do in these applications is essentially take energy from one form, convert it into the other. So AC to DC or DC to AC conversion. Everything that you see in your surroundings that have any power electronics in it has this AC to DC and DC to AC conversion, whether it is your fridge, your TV, your remote control, your laptop charger, your solar power or solar panels, and including your electric vehicles. Now, silicon has done an amazing job in making sure that it carried this power electronics industry till now. But as the requirements for efficiency and the size of these power electronic systems have come down, silicon is facing technical hurdles in just the capability of the material itself to be able to switch very fast. The golden rule in power electronics is the faster you switch a transistor, the smaller you make your power system. And case in point is your laptop adapter, which hasn't really shrunk too much in the last 20 years, and that's because of the inherent technology. Wide bandgap materials, and there are two main bandgap materials that are getting commercialized. One is silicon carbide, and other is gallium nitride. Are those materials that prevent this limitation of silicon of not being able to switch very fast and push the envelope to hundreds of kilohertz or megahertz of switching frequencies to be able to give you both an efficiency and size improvement in these power systems. Gallium nitride on gallium nitride is one way to utilize the properties of gallium nitride as a material to the fullest. When you have, for example, a GaN power transistor that many of you might have worked with, that gallium nitride transistor is usually going to be a gallium nitride deposited on a silicon substrate or a silicon wafer.
Yeah.
And just because of the nature of these two materials being different, you have a lot of inherent flaws or problems that come into the transistor that gets made out of it. I won't go deep into the device physics part of it, but essentially you run into issues where the device may not be fully robust, where you may have to use a non-optimal device, a bigger device, for example, for the application that you need. And it will prevent you from fully utilizing the properties of gallium nitride by not being able to switch it maybe as fast as what you could have. Vertical gallium nitride or gallium nitride on gallium nitride has always been in research papers touted as one of the ways to look into this and solve the problem. It is a hard problem to solve because gallium nitride is not an easy material to work with. So the work started back in UC Santa Barbara back in the early 2000s of creating the vertical gallium nitride structure. And we are now at a point after having gone through a couple of, companies that have tried to commercialize it. NexGen has taken a lot of that learning and developed a transistor which is using gallium nitride on gallium nitride, creating a pure vertical gallium nitride structure. And now this transistor is something that we are unveiling to the world that you can test in form of this particular board that you see here. So that's a brief background on what vertical gallium nitride is.
A very thorough one, I might say.
Thank you. Yeah.
So we talk about GaN probably been with us commercially for the last 4 or 5 years. We love the term disruptive technology at ipXchange because we're looking for alternatives to the mainstream. Nothing wrong with the mainstream. It's a brilliant place for electronics, but we're looking for things that are very disruptive. So with this, you use the term vertical GaN. So would that make you entirely disruptive in the GaN business where you're GaN on GaN?
Yes, absolutely. And the reason for the disruption comes in that nature of the transistor being vertical. So the transistor is essentially a gallium nitride wafer, and then we have a factory of our own in upstate New York where we grow gallium nitride using the standard MOCVD chambers, for example, and create this transistor. What that allows us to do is it allows us to control the breakdown voltage of the device just by controlling the thickness of the GaN layer that you deposit on top of it. What does that mean? So when you look at your electric vehicle has many of the current vehicles have 800 or 900 volt batteries. The transistors that you need to run that electric vehicle inside would need to be rated at greater than 1200 volts or even greater breakdown voltages, meaning you applied 1000 volts or 1200 volts across the transistor, and the transistor, if you don't want it to turn on, should stay off. And that particular portion for gallium nitride on silicon has been a challenge going back to the problem that I talked about, which is the nature of the transistor itself, because it's two different materials.
Right.
Gallium nitride on gallium nitride, vertical gallium nitride is able to go up to 4000 volts and even higher just because of the fact that there is no lattice mismatch or crystalline mismatch that is in the structure because it's pure GaN. Silicon carbide currently in wide bandgap material is the only solution available for these higher voltage applications. And the industry has been looking for now what's the next step beyond silicon carbide. Silicon carbide has provided a great alternative to silicon in electric vehicles. You see a wider adoption of electric vehicles because of that. But in order to really push the boundaries of adoption, you need a alternative to silicon carbide, which would be gallium nitride, that can cover both the low voltage and the high voltage segment. And that's what vertical gallium nitride does. And therefore, it is disruptive because it's the single wide bandgap material or single wide bandgap technology implementation that covers the entire power electronics market, not just a low voltage, not just a high voltage.
Right. So vertical GaN is the only one that sits between those two variants.
Correct.
Excellent. Okay. So you've mentioned electrical vehicles. What happens, when an engineer comes and says, I want to see what GaN-on-GaN does, what happens when they plug this in, they plug this evaluation board in? What would they look for? How would they go, wow, that is absolutely what I'm looking for? What would be the signals that they would get?
Yeah. So first and foremost, you will see vertical. So this is a double pulse board. It's a standard board that the community is aware of that is used to measure electrical characteristics of the device. The one thing that you will be able to quickly see and have that wow experience when you plug this board in is you'll be able to see the response time, the turn on and turn off times of vertical gallium nitride is much faster than what you would have seen with other devices in the past. With an order of magnitude of difference, right? Depends on the device, what the turn on and turn off time would be. But
and speed is important at that point because of efficiency.
Speed is important primarily because of the switching speed results fundamentally in the size of the device, of the overall system that you make. And by controlling the turn on and turn off times, you can potentially have lower energy on and energy off times, which could translate to efficiency. So to me, speed directly correlates to size. And with the right implementation of the system, by taking advantage of the speed, you get the efficiency improvements.
I see.
It is important to note that the device itself, vertical gallium nitride device, is a lot smaller, about 5 times smaller for a comparable RDS-on, comparable resistance or current rating than a gallium nitride on silicon device. What that does is it gives you a much smaller output capacitance, which, when you do the right system design, will enable you to improve the efficiencies quite a bit. We see a up to 3 to 4% improvement in standard topologies when you go from, let's say, a silicon-based design to a vertical gallium nitride-based design. And we have seen in the 2 to 3% range of improvements when you go from a gallium nitride on silicon design to a vertical gallium nitride design.
Right, right. And is there a cost implication? Because I mean, everything that we've said on this call sounds like, you know, if you're looking for the perfect solution, you need look no further than NexGen. So you know what, you know, from a design engineer, if you're being very honest, from design engineer, is like there cost implications for this very sweet spot, or you know, how does that work?
Right. So, like all new technologies, when they first come out, there is a price to pay because we haven't reached the economies of scale yet. And
Right.
this applies in everything that we use, you know, from a basic iPhone to a plasma TV. So similarly for vertical gallium nitride, there would be that initial price to pay because of the economies of scale. However, given that the device is 5x smaller, we see that as the volumes go up of our devices, we can actually start looking at matching or even beating the silicon costs, right? And this is a bold statement to make, and that's what we fundamentally believe in, that vertical gallium nitride is no longer at a point where we will be at cost structure that would be looking decent compared to silicon carbide or GaN-on-silicon. We are going for the gold, which is we'll be matching or beating the silicon cost structures.
I see. So that's a
And we
really
believe that
important that's a really important comparison.
correct.
Yeah. Okay. Good. Well, you've given me a fantastic introduction. We're going to have your board on. We're going to have your board on our booth at Embedded World, which is 4A556. And we look forward to design engineers coming in and having a chat with us. And they can apply for the board on ipexchange.tech. But been an absolute pleasure meeting you. Thank you very much for your time today, introducing vertical GaN, which is a phrase that I have now learned, which I didn't know beforehand. So hopefully we can spread that term to our community, and we look forward to the progress of GaN-on-GaN technology with NexGen. Thank you very much.
Thank you so much. It's a pleasure. Thanks.